then, and I checked to make sure that you could hear me. So it looks like we're good to go. I'm going to go ahead and also charge the computer just in case it falls asleep. It won't fall asleep if it's charging.
You're so
Maybe. Okay. Wait, Julio's in. Oh, hi, Julio. Are you joining from home? Oh, yeah, 2020. Julio's here. As a blank screen. I don't know where Julio's at, but maybe he will type and let us know. Or text Alina. Alina has your wallet, and I'm going to just message that to him. Julio, Alina has your wallet and what is it? Apple iPods? Apple AirPods?
Just AirPods, but not from Apple.
Oh, so AirPods. Okay, so let's go ahead and get started. Everybody pretty much got the points here. And this mechanism you're going to actually see in today's lesson.
Julio says he doesn't have a microphone.
That's fine. You can type in the chat. That's what people did back in the day. They would just type. They don't have to talk. I haven't muted anyways. Anyways, so this is actually a mechanism we're going to see today. But in this specific question, they gave you enough information to figure it out, and I saw you all figuring it out yourself. So CH3, Cl plus AlCl3, even though this isn't Cl2, you could do the same thing here, where AlCl3 takes the chlorine. This part becomes positive, which they tell you, and the AlCl3 becomes AlCl4 and negative. And so if we did that, you got a point. That was the first point. The mechanism, there was some confusion with. It took some double checking, triple checking, maybe quadruple checking to see if you got it right. You're supposed to always start mechanisms from a pair of electrons to a positive charge. When you write a curly arrow, and you may want to write this as a note for yourself, curly arrows always start at pairs of electrons. And in this structure, the pair of electrons has to be coming from the pi electrons in benzene. So that's where we start the curly arrow. So we do that to CH3, we get this. And then we get CH3, and you should write the hydrogen there. Right now, this was 1 point. This is 1 point. This is 2 points. So what's the third point? There's 3 points here. I saw some of you were more illustrious than others on this. At bare minimum, they accepted as you just take those 2 electrons and fold them down to the ring. They accepted that. Technically, though, we know that the reason that happens is because this takes the hydrogen, and then those 2 electrons come down. And I saw some of you included that part, that it was actually the AlCl4, those 2 electrons on the chlorine, grabbed the hydrogen, restored that, and then you get the restoration of the ring here. But at minimum, as long as you drew that 1 arrow from the pair of electrons and hydrogen down, they'll give you the mark for that. And this is a recent test, actually. This is from the past couple of years. So this is actually pretty kind in the grand scheme of things on getting marks, because think about other questions that have been worth 3 marks that are like a whole page of math. This is also 3 marks, and you wrote like 3 arrows and 1 structure. So when you're studying for the end of your exam, make sure you're considering like how many marks each thing is worth and what you're able to do easily. So these paper 4 questions had some AS chemistry involved. Find your AS chemistry flashcards when you get the chance. I will be spending some time during these class periods going over some AS chemistry reactions, as we are also going through organic reactions. Just to remind you of sets of reactions you should remember. And also, we are going to start a little competition next week. Which half the people won't know it about until the class before, so they'll have 2 days to prepare. All right, so a 3-step synthesis of phenol ethanoic acid is shown. They ask you reagent and conditions. This we went over last class. because the bromine is not adding directly to benzene, it's adding to the carbon outside of benzene. It has to be Br2 and UV light. You have to give both your reagents and conditions to get the 1 mark. Suggest the structure of compound Q. This is the hard question. That when probed, some of you were like, ah, you got it. The key here was to recognize compound Q is in between these 2 compounds, right? It's what you have to get in between. There's 1 carbon in the answer for step 1, but there's 2 carbons in the answer for step 2. There's only 1 reagent that can add a carbon. And Roslyn got it first. It was cyanide. Cyanide, which is Cn minus, will be the thing that does that. Which means that our structure here would be Cn. And you could just write it like that. Or it's 1 more carbon. Yeah, like that. Because we have to have 2 carbons on the answer, right? So that would be it. The conditions for both of these steps are actually heat under reflux. So heat under reflux or heat they accepted, but some of them have to be reflux, so I would just usually do heat under reflux just to be safe. I saw some of the mark schemes, they went heat/reflux, like you could write either. I would just say heat under reflux. So then step 3 would be what? To go from Cn to COOH was a very specific reaction. You needed to use acid. And so what acid you chose doesn't matter. So some of you chose HNO3, H2SO4, HCl, or you just said acid. So as long as you wrote any H plus strong acid and wrote heat under reflux, you would get the mark there. So this was 8 points on a paper 4 from organic. All right, so let's get to today's lesson, which is technically a continuation of last class's lesson. We're still working with reactions in benzene, and we're also going to be starting into phenol. So, Unit 6, Part 3. These are our objectives. We're going to be going over nitration today, which means how do we get NO2 on a ring? We're going to be going over something called the Friedel crafts, and that's the scientists who came up with it. But the key word here is alkylation, which means we're going to learn how to add carbons into a benzene ring. Technically, we've already done it in the Bell work. That was the Bell work question, was we added a carbon to the benzene ring. So we've already seen how to do that. We'll practice that again. And then acylation, which is adding CH3COCl and acyl chloride. And this will add you a carbonyl into the ring. The catalyst being the same catalyst that you use for all of the substitutions on a benzene ring, AlCl3, or it could be AlBr3 if I have bromine. So if this was CH3Br, what would my catalyst be? If it was CH3Br instead of CH3Cl, AlBr3. And instead of using aluminum, what is the other variant of the catalyst? Like, what is the other metal we could use? Fe, right? So they're showing you the one with aluminum, but you could easily do Fe instead, and the same thing. And then it also says we need this reaction to oxidize, complete oxidation of the side chain. This means the chain that's off the benzene ring. And KMNO4 is back today. We haven't seen KMNO4 for a long time, but that's one of our big oxidizers. It's what we use to oxidize. So we'll be looking at what KMNO4 does with benzene side chains. Hydrogenation. We've heard of hydrogenation before. Do you remember that one? Back in the day, it meant add hydrogens. The conditions are the same as they were back in AS chemistry. So we can actually hydrogenate a benzene ring by using H2 and platinum or N-nickel catalyst. Then finally, we're going to start talking about phenol today and start getting to reactions of phenol versus regular benzene. And so we got a pretty good day today. Let's talk about schedule. Last night I was working on what our schedule looks like for the end of this unit. So this leads us up into when we start studying for our Cambridge examination. That means after April 8th, we are in review mode, meaning we're studying for end of year exams. So March 7th, that's today, we're finishing reactions of regular benzene and we're going to start talking about phenol. Next class, we're gonna do reactions of phenol and carboxylic acids. The next class, next week on Thursday, we're gonna talk about reactions of acyl chlorides, and you're gonna have a team competition, which I will be revealing to you next class, the exact way the competition works. But all I'm gonna tell you for now is start studying all your reactions.
It's just
No, because last year you did individual mini assessments. This year you are gonna be in a team. No, do you prefer tests?
no, it's okay how it is.
Would you like an individual mini assessment? I could change all those team competitions to quizzes.
No.
I thought team competitions would be nicer. I'll reveal the team competition like next class, but expect to be in teams of 3.
3.
Yeah.
3.
Yeah.
We got a troll in your team.
I can't do 2 because we have an odd number of students. Like it would be 2, 2, 2, 2, 1.
Yeah, we got it.
So it's gonna be 3, 3, 3, and 2, but the 2 will have like what I'm doing for the AS class. They'll have like a ghost student, and so what that means is whatever the average is, that student like whatever the average of the class is, that third spot would hit that average. So it's gonna be like that. The teams will be teams of 3, so expect that, and I will try to accommodate your preferences for teams. I know there are some ready-built teams of 3. But it will be teams of 3. And it will likely go off of your quarterly exam scores from the past. So that means that there can be no super team. The top 3 students of the class cannot form a team together.
Thank God we don't have that problem. Don't worry, I get to pick the
Damn.
class average.
I'm just saying, in my AS chemistry class, I had to do that as well, where no super teams. Because I've tried team competitions before, and the reason I didn't give you a team competition last year was because the last time I did a team competition 3 years ago, a super team formed, and they just destroyed everyone. And so, for that reason, I will accommodate your preferences as much as possible, but I will be putting like only one student that gets high scores on their quarterlies in each team. So,
Are we good then?
FYI,
Sounds study.
Okay, that's that.
because you need to help bring people up. All right, so there will be 3 days of a team competition. You'll see them March 13th, 17th, and 19th. And I am debating, currently thinking about what the top team wins. But expect it to be similar to the AS class, which their first place team is getting public subs.
We might have to drop it.
And a 20% boost on their unit exam. Yeah.
Yeah, we're dropping it. We're dropping.
You may not have a choice. You can't form a super team. So that's why I said I'm gonna pair people together. Like I said, that I will try to pair people that are friends together, like I did for AS chemistry. But it can't be a super team. Like I said, you have to help each other, bring each other up. You'll work together. I'm not gonna reveal to you the style of the team competitions, but expect whiteboard games to be within the realm of possibility.
I'm gonna read on you.
Expect whiteboard games to be, because I have to make them. Like basically, I have to make this all. So whiteboard games, expect possibility for some of the Kahoots that we've played, like that we've tested out, like to be types of competitions. And so I'll be working through what they each are, but I'm giving you a heads up that it's coming it's starting next week, but not next class. Thankfully for those people who aren't here, because they wouldn't know. It'll be the class after. So those students will have a bit of an opportunity. I don't know if Julio can hear me from here, but those students will have a bit of an opportunity to catch up on anything that they missed. So March 21st, which I've just been informed that some people were planning to miss school. That's the day of your quarterly free. So I hope they don't, because that will replace the lowest grade for the quarter. So if you didn't do well on the Unit 5 exam, the quarterly free is where it's at. You have to do well on it. And there is no other opportunity to make it up unless you make it up before March 21st, because that's the last day of the quarter. Quarter 3 ends on March 21st. So FYI, heads up, We're starting quarter 4 when we come back from spring break. All right, so yeah, you're good, close to the end. And we'll also be close to the end of the material because there'll only be one lesson after that when we come back from spring break. We'll have one final wrap-up lesson, and then we'll have a review day, April 4th, for just this unit for organic. And then on April 8th, we'll be taking the organic exam. So the quarterly is going to have everything. It's a full paper 4. It'll be a full paper 4, one random paper 4 that I selected, which means it's going to have anything and everything from the whole entire school year. So I'm also giving you a heads up, start prepping for that. That's going to be taking place when? March 21st. And so April 8th will be your Unit 6 exam, which is organic. And then after that, we just go into review mode studying for our paper 4 and 5. We'll be starting with paper 5 because we've spent all of our time this year on paper 4. So we will need to go over, what is paper 5. Paper 5 is less marks, but we'll need to spend some time going over what are the exact requirements for paper 5. So we'll do that after April 8th, once we finish the core content for the class. All right, that's the schedule. Yes.
Full paper 4 is the 100 marks.
It's 100 marks in 2 hours. That's what paper 4 is. When you take paper 4, it's 100 marks in 2 hours.
Who's the worst?
Next week, if you want, what I can do is I can, by the end of next week, so not next class period, but the class period after, give you a couple practice paper 4s that you could have, like just the practice to work through with the answer keys so that you can go and check over. I'll print some out for you so you can prep over the weekend before and practice. All right? So, yeah, full paper 4, it's going to have everything. From acids and bases all the way, it's going to include what we're learning now. Because you'll notice we'll have almost be done with everything. We're literally just missing one small lesson. All the content will technically be there for that quarterly. We'll have done everything. So, FYI, that's what's coming up on the schedule. All right, so now that you know what's going on, let's get into today's lesson, which, like I said, was predominantly just a continuation of what we did last class. Your flashcards. You're welcome. I bought those for you. It is a project grade, which will be due on the day of your Unit 6 exam. And basically, I'm just checking that you did the flashcards. This is to help you practice just like last year, with your reactions. And so I do expect, as we are going through the class, when you see a reaction that's new, you're going to put it on your flashcard. That way you save time. You don't have to spend time outside of class doing it. I try to do as much within the class period as possible. There are already 5 reactions we covered last class. So make sure those 5 reactions get on your flashcards. Today, we're going to start with, nitration, technically, but that's a review. So let's take a look back at this mechanism. We saw it in the bell work. The mechanism for electrophilic aromatic substitution is always the same. You generate your electrophile, then your benzene ring grabs the electrophile, then you fold down the hydrogen. It's always the same. So, nitration. Let's talk about nitration. I think you should probably make a flashcard for this. So I would put a flashcard for the generation of the electrophile reaction. Why? Because I think it's difficult to remember it otherwise. This is something I would have the front on one half of the flashcard and the back on the back of the flashcard. So how do I get the electrophile I need? I mentioned it last class. You have to put together nitric acid and sulfuric acid, both concentrated, nitric acid and sulfuric acid. You put them together, and sulfuric acid is so strong with nitric acid that it actually breaks the two apart. And you get this electrophile, NO2+, as a result. So sulfuric acid acts as an acid, nitric acid acts as a base, and you end up with the products that you see there. Sulfuric acid is so strong, it forces HNO3 to take on an H+. So in this reaction, sulfuric acid is actually acting as the acid, and nitric acid is acting as the base. How do I know that? In the products, you get HSO4-, and you actually originally get H2NO3+. But this doesn't stay together, it falls apart. And so when it falls apart to become NO2 plus, and it becomes H3O plus. And it's not balanced, but that's the idea of what happens. So this is an acid-base reaction. When you put sulfuric acid and nitric acid together, sulfuric acid forces nitric acid to receive a proton. But it can't hold like that because that's not stable. So it falls apart. So
an
you
acid
get-
can react with an acid.
Yeah.
When the lower acid reacts, is gonna.
It has to be as a base, yeah. So this strong acid can react with this strong acid. This strong acid forces that one to take on the H plus, but it won't hold it. So it actually causes the whole molecule to break
So the
apart.
reaction, the base,
The base
Yeah.
here is nitric
the
acid,
acid-base reaction of two acids results in at least three.
3 products. Yes, 3 products. And then here, these products are ones you have to remember. Why? Because the NO2 plus is the electrophile you need to nitrate the benzene ring. So once you have generated the electrophile, which this would be a 1 mark, like this would be a 1 mark question, just like we saw in the bow work. It would be 1 point to give that reaction. And then from there, it would be the mechanism. And how many points is the mechanism itself? It's 1 mark here. 1 mark for this, right? And then 1 mark right there for that, for the hydrogen folding back in. You don't have to write as many curly arrows as they write here, just like we had seen in the bell work. What would be the accepted by Cambridge? Because I run this again, I picked this up online. So what would be the Cambridge acceptable minimum amount of work for the marks? Benzene ring plus NO2 plus. What grabs the nitrogen? So it's going to be the same overall style of mechanism. What grabs the nitrogen in step 1? A pair of electrons, which is coming from the benzene ring. So you start by grabbing the nitrogen like that. That's worth a mark, if you can remember that. Then what do you get? The way that Cambridge accepts us to write our product here is to write a incomplete ring with a positive charge. We would have the NO2 on one of these carbons. It doesn't matter which one you put it on. It's equivalent. And you have to write the hydrogen on the same carbon. Why does that matter? Because those 2 electrons from that hydrogen are going to fold back into the ring always. Because that hydrogen gets grabbed, in this case, by water. And that's where you're getting the H3O plus, part of where you're getting the H3O plus. The water, like it shows there, 2 of these electrons grabs that hydrogen, that goes back into the ring, and you get this NO2 plus H3O plus. So just like the mechanism you saw in the board, it's going to be 1 mark for the actual equation. I think this is one of the harder equations to memorize. You have to remember the exact amount of atoms with the balanced equation. So it's HNO3 plus 2 H2SO4s makes NO2 plus 2 HSO4 minus plus H3O plus. And then this is the mechanism. This is the way that I found it from an image online. And then this is Cambridge accepted answer with the ring instead of the 3 double bonds. How many unique mechanisms did I tell you there were going to be this year? 2. This is the same mechanism we've been talking about. This is not a unique one, right? This is, everything we do today is going to be all on the same mechanism. We're not going to see the other mechanism until next week. So nitration, bromination, chlorination, alkylation, and acylation. All 5 of these processes we're learning are all the same mechanism. It's get the plus charge thing. The ring grabs the plus charge thing, and then you have an intermediate, hydrogen folds back down, and you get your restoration of your ring. These are what type of reactions? Is this an addition or a oxidation or a substitution? So every single one of these that we're doing are substitutions. Meaning the hydrogen's getting off of the benzene ring and whatever group we're replacing is getting on to the benzene ring as a result. So that's the mechanism of nitration. I do advise making a flashcard for the generation of the electrophile in nitration. We're gonna go ahead and move on. All right, so the next one we saw on the board. However, you should make a flashcard for it. The next one is called the alkylation reaction. So what happens here? So this you should have a flashcard for. This is the reaction to add a carbon chain to a benzene. So it's a substitution, but if I want to get a carbon chain on a benzene, this is the substitution I'm going to do. And so you should write that in a flashcard. I'm going to give you some time and then we'll look at some examples. It's called alkylation because alkyl groups are R groups. That's why we call it alkylation. This is actually the reaction we saw in Bowick, where we're trying to get carbons onto a benzene ring. And so you need the same catalyst that you would have for, and I think this part down here isn't absolutely essential. You don't have to include that. You cross that out if you want. But what's absolutely essential is that you have the catalyst. Just like adding Cl2, just like Br2, here you need the same catalyst. So either AlBr3 or FeBr3. So then what would examples of this be? What would your product for this be? I'll pause to give you a little bit more time, and then I want you to look at the board to look at a couple of examples. So notice what it says here. Whatever the R group is, adds to the ring. What's the R group here in this first example? So how would that add to the ring? In which direction? What would you write first? The CH2, right? Because CH3 has to be at the end. So if this is RCl, then this is what's adding to the ring, like at the CH2. So this would be CH2, CH3. Does that make sense? Let's try again. What about this? Spice it up just a notch. How would this add to the ring? Here. Where would the R group add? From the CH, right? Because that is going to be where the electrophile is right on that carbon. So then what would our product be for this one? CH, right? CH3, CH3. I'll give you some time to see if that makes sense, how I did that. So I'm attaching wherever that halogen was at, that's where I'm attaching the carbon chain to the ring. Make sense so far? So this is how I get carbon chains on a benzene ring. You have to have a halogen alkane to do it. Once I see everyone's pretty much done writing, I'll continue. On the next slide, what you're going to see is a mechanism. We have done this mechanism before in the bell work, actually, but just with a slightly different example. So I'm going to go through it slightly quickly after everyone's been writing here. If you're good, let's take a look at this. Acylation. So what's the difference between alkylation and acylation? What is the difference? And I want you to underline this because there's a key in difference in alkyl and acyl. Acyl means this. You're adding at the carbonyl. So in an acylation, instead of a carbon chain, you're actually going to have a C double bondo and then a carbon chain. So that's the difference between alkylation and acylation. You will need a general reaction for this one too. So I see that I've given you an example here, but let me write a general for you. Because remember, the general reactions are what you should put on flashcards. So a general reaction for an acylation. Start with this. The requirement for the reagents is you must have an acyl chloride. Do you remember what the acyl chloride was? This is why they call it acylation. Acyl chloride is COCl. Whenever you have COCl, you have a acyl chloride. So you have to have an acyl chloride. And then what is your catalyst here? The very same catalyst for all of the electrophilic substitutions. So what would that be? AlCl, right? Or FeCl3, one of those two. So you need that catalyst because the mechanism is going to be exactly the same. And then how would it add for the general? You would get this. It doesn't matter where I add it. I'm going to add it here. I would get this and then R, whatever my R group is. Noticing that I'm always adding where the double bond's at, that would be the carbon I'm adding to the ring. So you should write this on a flashcard. Not the example, because the example is like one specific example. This will work for all the reactions. While I'm waiting for you to write this flashcard, Just saw it pop up on my phone. Did you all see the thing in the sky last night? Did you see that the SpaceX like rocket exploded in the sky over South Florida? It was actually like if you look in social media, there were posts, but yeah, it was all over like Nextdoor and the Ring app, and it was over Key Largo.
Oh.
So, but you could see it from Homestead. Like people in this area were like posting pictures of the sky, and it looked like there was like a portal that opened in the sky.
Close to red, so I probably didn't see it. If I was outside, but
You would have seen it if you were outside. I was not outside,
I felt
so I did not see it. Oh, we were still doing the Olympiad at 4, so yeah. But I could have seen it. I just wasn't.
Oh,
You were ring ceremony was taking place at the time where it happened, but it was something that took off from Texas. But apparently, where it exploded was like right around Key Largo. So they had like a ground stop on all air for hours last night. So there couldn't be any air travel at Miami International Airport because of like the debris that they were worried about was falling down. That was just you're just in space. So it's an interesting thing that happened. They keep exploding though, so
Yeah, you saw like happened in like other states. I didn't know what happened here. I really want to see it.
those rockets keep exploding, meaning that there's something in their construction and their engineering that's wrong that they're trying to fix. it's because the engineers are graduating with ChatGPT.
That's not know.
That means it's gonna get worse.
What? Just don't say
Justin.
Justin. Yes.
Yeah, he's doing possibly a summer program like with NASA.
Watching the yeah, I signed up for it. It's pretty much.
Good. The hospital?
Yeah, I signed up to volunteer at the hospital.
All right, did we get this? Or we're almost done? All right, let's take a look at a couple examples then. Like, how would this look? An example. What if we had
I'll hold you down.
I feel like he was depressed today. Right after.
Oh, it's okay. No.
It's okay, your blood test came back really bad.
It's like, it's the worst I've ever seen. Okay, it's just like, yes, that's what matters, no?
You maybe have 6 months to live.
Exactly. Man, if it's not malpractice, I'll just make all my patients depressed. They could be depressed about it. But they're on yes. Isn't therapy good?
So what will we get here? Where does the carbon attach to the ring? From where?
Yeah.
From the CO. So that's what you have to remember here. It's always from the CO because the chlorine's going to go with the FeCl3. So this is going to be the electrophile. So we get this. If it attaches CO, how many more carbons after that? So it's CO, and then how do we write it? CH2 and CH3. Are you allowed to write skeletal? Sure. You're absolutely allowed to write skeletal. If you prefer skeletal, write it that way. I also want to show you the example here. Notice the example here. It's methylbenzene. Do you remember from last class what methylbenzene does? The methyl group is a director. It directs to the 2, 4, 6 position. Do you remember that? Barely. So I'm reminding you.
Thank you.
So CH3 is a director, and yeah, when you start the team competitions, those kind of questions will be at play.
Oh. Continue on listening.
So then you have, yes, go ahead.
So for the example that you showed us, the
Yes.
CL is no longer part of the reactor. For
Byproduct.
the CL2. Oh, no.
Just like before, it would be like that, where you would get that. You would get a byproduct of HCl. You're welcome. So director, what would direct to the 246 position. Notice how this image that I grabbed online only put it at the 6th position. Could you reason, or sorry, the 4th position. Could you reason why possibly it would be best to put this group on the opposite end and not right next to the carbon? So the idea is that electrons repel each other, right? So if groups can get as far apart from each other as possible, they will. And so if I have a large group being added, a large group of atoms will typically be favored to add as far away as possible. So that's what's going on here. That's why they show it to you in the 4 position and not the 2 or the 6. Because typically if I add a large group of atoms, you should add them as far away from groups of atoms that are already there as possible. And so that's why you see it at the, I want to call it para position, but we don't use that terminology. It's the 4th position. 2, 4, 6. So you should write that down just because it helps with understanding why they put the answer here like they did. So once again, I wrote here, large groups of atoms are favored to add as far away as possible. So because this group was here, I would say, because this is a large group of atoms, that it should add as far away as possible. So if it had the options to add 2, 4, 6, 4 would be the best one to add to. You'll still get some at 2 or 6, but 4 would be the best one to add to. We'll go over this mechanism one more time, and then you're going to try one. I'm going to show you 11 and 12, slides 11 and 12, and then you're going to do number 10. 10's a little bit easier. So I think that would be the way to go. I'll show you 11 and 12. We're good? So I'm going to skip this one because this is the one I'm going to ask you to do because it's a little bit easier. I'm going to show you this one because it's from a paper 4. This is one of the steps to manufacture a medicine called ibuprofen. Have any of you ever taken ibuprofen before? I have some in my drawer. Sometimes if you see me with a headache, I'm just like, okay, let me try to run around with my day. Headache medicine. Ibuprofen is used for pain relief to block pain receptors. So although you still have pain, you just don't know it. Like, it's literally like throwing a Band-Aid on the problem and kind of trying to ignore it and hoping it goes away, which is what a lot of medicine is for. Is like hoping, you know, it's gonna
Just letting your body do it.
let your body work, but hopefully your brain doesn't know like anymore. So you give yourself some drugs to make you feel better, right? So ibuprofen. It's a drug, isn't it? Medicines are, generally speaking, drugs. Yes, everybody. Well, not everybody, but I'm assuming most people do take some form of some type of drug. The classified drug that most people take, you know what it is? The big, like the most consumed drug in America.
I know.
No, I don't. No. Caffeine. It's classified as a drug. It's a stimulant.
You don't take opium, bro?
Because of all the coffee
That's like
that
drinking water.
people like myself drink. And that is the drug that is the most
You don't want
consumed by the American population.
Legal drugs are allowed.
It is legal. Yes, legal drugs are allowed. Ibuprofen is a legal drug.
Legal?
Legal. Legal. Oh my God. All right. So one of the steps in the manufacture of ibuprofen, they're showing it to you here. And they ask you write an equation for the reaction between CH3COCl and AlCl3. What do you think? And I'm going to write it up here first. What do you think happens here? Think about the bell works. Think about what we did last class. What is AlCl3 always going to do? It's going to steal what? It's going to steal a chlorine. So you end up with AlCl4 that has a minus charge. And then what would the other product be? If this loses its chlorine, what charge would this carbon have? Would you agree that it would be positive? You might call it positive. But positive, yes? So then our reaction would be, and I'm just going to write it in structural form because we don't have enough space to write it in displayed form. Cambridge will not give us enough space. And so I just wrote my work here, but then it's CH3CO plus AlCl4. Mike, do you see how that works? Every single time the catalyst does the same thing. It takes the chlorine or it takes the bromine and then leaves a cation at the end. So this would be 1 mark. On the next slide is the actual mechanism. So it says here, complete the mechanism, but I wrote it on the next slide because there's not enough space here. So they want you to change this into this. They're telling you to go this into this. Why again am I putting this on the 4th position, not the 2nd or the 6th? I mentioned, because like, look, this is a big group here. And I'm adding a big group. It would actually, these two would like interact with each other if I put them too close. Does that make sense? And electrons repel each other, so it goes the farthest away that it possibly can. And so that's why you see it showing up on the opposite end. If it was a small group, it would be much easier to put it on carbon 2 or 6. But here it's going to go to 4. All right, so they say complete the mechanism. They gave you the start, they gave you the end. You have the electrophile. Let's take a look at what we would need to do. Same 3 marks. What's the first thing? What is the first part of this mechanism? The CH3COCl. But we already did that. We had that, right? So we have, this is the electrophile. We need to start with that. We have CH3 C double bond O plus, right? We start with writing that. I don't have a mark yet. What's the first mark we're doing?
An arrow from the pair of electrons.
Right. So mark 1 is the pair of electrons in here. It's written as a circle, so you just assume 2 of those electrons from the ring are going to where? Where do they have to go to? It has to go to that carbon. The one with the positive charge. So that's one of the marks, if we can do that. 1. I'm writing the numbers so you know where they're at. They're very predictable how to get them. What's our next thing to do? What's the second mark for in this mechanism? Something called the intermediate. So this is still there. I can't lose that. I have a broken benzene. It's a broken benzene. And where do I add the COCH3? It's a specific spot. It has to be added. It has to be added right here. Do you agree? It has to be like that. So far, so good. This is my second mark, is for writing the intermediate correct. Where's the third? H. There's an H. Where's the H? It's always on the same one that you had added the group to. That's where the hydrogen is that needs to get gone. How does that hydrogen get gone? Technically, your catalyst, which is the AlCl4 minus that's hanging around there, right? That was present, that is hanging around there. Grabs the hydrogen. And then what happens to the 2 electrons here? They transfer back to restore the ring. So instead of a broken ring, you have a complete ring. So this would be the third mark, is to show that curly arrow. And so then your final response here would be just the product, which is this. Wait, I'm missing a part again. Like that. That. And then on this side, it would be, if I wrote this skeletal, how would I write it? It would just be a line coming out, right? You could write it structural or skeletal, your choice. So it could be like this, or you could just write it like this, the way that they present it to you here. It's the same thing. Did you see how to earn the marks here?
So all of these reactions we're talking about are the same literal exact mechanism again and again and again. Analyzing the past decade of paper fours, on about 80% of them, this is the mechanism you get, the electrophilic. Remember, there's two major mechanisms. On 80% of the paper fours that I've seen, this is the mechanism that you get because the most types of reactions utilize this exact same mechanism. And maybe like 10 or 20% get the other mechanism, and then 10% get something from AS, like one of the mechanisms from AS. But this is the one that shows up most of the time, the electrophilic aromatic substitution, or they just call it electrophilic substitution. All right, so we're done with that. Electrophilic substitution, done. Now we're going to talk about some of the other reactions with benzene and then talking into phenol. So the next one goes on a flashcard. It's one of those flashcard reactions. Here we go. Hydrogenation. So the general reaction for hydrogenation of benzene, it's actually one of the only things that benzene does the same as alkenes is you can add hydrogen to it. And what will happen when you add hydrogen to the benzene ring, so plus, and I would write excess H2. It's 3H2 to make it exactly balanced, but I would write excess H2. And I would write nickel or platinum, because that's how we saw it in high temperature heat. You do not have to memorize exact temperatures and exact pressures. I pulled this up from an organic structure from online, but it's not from Cambridge. So you do not have to memorize the exact temperature, the exact pressure. So the way that I'm writing it is how you need to know it for Cambridge. Nickel or platinum and heat. The product, all the double bonds go away. You add hydrogens to everything. So instead of benzene, what do you end up with your product? Cyclohexane. So basically, all three double bonds are, that's why it says 3H2 here. Because you add hydrogens there, you add hydrogens there, and you add hydrogens there via a typical addition reaction. And you end up with cyclohexane. Only with platinum and hydrogen. That's another way of looking at it. You're adding hydrogens to all the double bonds. So what type of reaction is this? Is it a substitution? No, this is an addition. So type is addition. Because you're adding to the double bond. And this is one of the only reactions, like I said, that alkenes and benzene do the same thing. Because alkenes and benzene usually don't do the same thing. But for hydrogenation, it works with both. So you can make benzene into a standard cyclohexane this way. You want this on a flashcard because this is one of the reactions that's commonly tested. There is another reaction coming up that's a little bit stranger. So this one's not strange. This is actually something we've seen before for alkenes, exactly the same thing. The next one, when you're ready. Still see some writing, so I'll pause. So we could call this addition, or we could call it what? While I'm waiting? Instead of addition, I could just call it hydrogenation. Because I'm adding hydrogens. And when you see hydrogenation in your nutrition labels, that means it's added hydrogens via this process in a chem lab, in a science lab. Hydrogenating your food, hydrogenating your oils. Yes. Because saturated fats are but not saturated fats. But it has a longer shelf life, so there's a trade-off. So it's bad for you like over a long period of time if your body stores it, that does cholesterol. Then you get heart attacks. But unsaturated fats spoil fast. So like if you eat an unsaturated fat and it's spoiled, then you're gonna get sick quicker. But it's gonna be more like gastrointestinal, throwing up kind of deal. Food poisoning for bad food. Like what? Butter? You won't get that from butter. Doesn't
Butter saturated. Like, if you eat a really old avocado, you would never, but it would make you sick. You know from the color change not to eat it. Like, once it turns that brownish black, don't eat that avocado. All right, continue. The next one, so this gets its own flashcard as well. Bunch of these reactions that were in our standards today. This gets its flashcard as well. If I want to oxidize the side chain of a benzene ring, so I'm going to write a general reaction, and I want you to write the general reaction. Once again, these are examples, but the general reaction is what you should have on your flashcard. The general reaction is the following. We're going to get benzene ring with a circle. You can do the 3 double bonds, but I just want you to be familiar with how to do it with the circle. And let's say you have any R group. It does not matter, and this is a really weird, big deal. It does not matter how long that carbon chain is. I'm assuming within reason. 1 carbon long, 3 carbons long, 5 carbons long. If you add KMNO4 with specific conditions, which I put in the arrow, to reflux, and then OH minus. So it says alkaline. Alkaline means OH minus. So just to bring that up, alkaline means OH minus because alkali is base. And then, so step 1, reflux OH minus. Step 2, H plus. Then what will happen? So you should write those conditions on your arrow. So the first thing is reflux with OH minus, or heat under reflux with OH minus. And the second is you add acid. So that's why you see me write H plus there. So this is 2 steps. What will happen is you actually get this as a product. You end up with benzoic acid.
There's nothing with it.
No matter how long your carbon chain is, it will change straight to carboxylic acid with this method. So potassium permanganate, OH minus, and then once that's done, you acidify. And then there's a couple of examples here. Notice this goes straight to COH, but notice this, even though it's 3 carbons long, also goes to 1 COOH. So the product's always the same. The product's always just benzoic acid, no matter how many carbons it is the key thing here. 1 carbon, 2 carbon, 3 carbons long. So if I have this as another example, plus KMNO4, OH minus, reflux, and then acidify. What would my product be here? Benzoic acid. So the neat thing about this reaction is the product's always the same. So this is called oxidation of the side chains to produce benzoic acid. And you just need these specific conditions for it to happen. So this is your KMNO4 reaction this year. This is what KMNO4 does for you. Once again, this is what you should put on a flashcard because the general reaction is what you need to remember. It doesn't matter what the R group is, just that you know it's an R group that does this. KMNO4 OH minus, that's a carbon chain. The whole carbon chain goes away.
The only thing that stays is
Is-
the initials carbon.
Exactly. Everything else is gone. And then it replaces with OOH. As I said, it's a nifty reaction. And they found if they did these specific conditions, they would get specifically benzoic acid every single time. All the other carbons go into the solution.
What about 2 benzenes?
What do you mean 2 benzenes?
1 benzene. Yeah.
Interesting. Naphthalene. Naphthalene, I'm sure, has its own unique reactions, but if you had naphthalene, if you had naphthalene
and you had that plus KMNO4 under the same conditions, you would get naphthalene with a COH on the end. Naphthalene, by the way, is a double benzene ring, and it is, if you've ever smelled mothballs before, I don't know if anybody's ever smelled mothballs before. I remember it because my grandmother kept mothballs in her house to like prevent stuff from eating through the clothes. Have you ever had holes in your clothes? Like you leave them in a drawer and then you have a hole in your clothes? Could be from moths eating your clothes. Like if you have a random hole in your clothes. Well, my grandmother, I lived in the Everglades, okay, y'all? But my grandmother had mothballs and it has like this pungent smell. You should bring them in one time.
Oh.
See? I did one time when I, like several years ago, I brought in mothballs to talk about with my A-level class, and then the poor Prius kids were like, what is that? Naphthalene. Bubble benzene ring. It has a really pungent smell. Like it smells, it's a distinct smell. You will never smell it anywhere else. But the answer to your question is, yeah, this would make a double benzene ring, right? That is a terrible benzene ring. Worst benzene ring ever. And then this would have the COOH like that. So something like that. All right, so let's try a couple of questions. Copy and complete the two equations, which could be used to show alkylation and acylation. And it says mono substituted products, so that means we only want one product. Mono means one. So what would this be, this first one? And I'm not gonna write the structure, I'm gonna write a skeletal. So C6H6 is benzene. And then what do we got going on here? Plus, okay, so you could write it like this, 1, 2, 3, and then Cl. So I'm just rewriting it. What's our catalyst? Gotta have the catalyst. AlCl3, right? And so what would our product be here? Benzene ring. How many carbons do I add? Like that. So if I do skeletals like this, or I could do CH2, CH2, CH3, it's the same thing. Typically with benzene rings, they're okay with you writing skeletal. You do not have the right slate for benzene. Ever. All right, then this next one, what would that be? I'm rewriting it. What am I mixing this benzene with? That's an acyl chloride. So that would be, how many carbons long it says? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this is the same thing as that. What's the catalyst that I need? Or it's not going to happen? AlCl3 or FeCl3, because it's chlorine. If it was bromine, it would just swap from chlorine to bromine. Same ideas. And our product now would be what? It always attaches right there, right? So it's going to be C, double bond O, and then you just have to count your carbons. How many was it? How many altogether, including that one? 5. So 1 we've already written. So then 2, 3, 4, 5.
So we can do CH2 first.
Yeah, CH2, 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 CH3. Always CH3 goes on the end. CH3s always have to be the end carbon.
Just connect the one closest to the Cl, right?
Yes. So it always connects from here.
And can it connect if the Cl is halfway into the chain? When it split into 2?
So if the Cl, like this one, was halfway to the chain, then your product would look like, let's say that it was this plus this, simple one. Then this is where the electrophile is. So your product would be like that. Does that make sense? It connects wherever that electronegative group is. That's where the positive charge is created. That's where it attaches to the right. Yes? All right, so try another one. Give reagents and conditions needed to turn benzene into cyclohexane. This is one of those common Cambridge questions. They ask you for reagent and conditions. What do we use? Nickel and heat. Okay, that's conditions.
what do we actually got to do to turn benzene into cyclohexane? If we don't have the reagent, we don't have the reaction. H2. So conditions are nickel and heat. And then reagent is H2. That's the thing we have to add in to the ring, right? And what type of reactions did I say that was? This comes from the Cambridge text. Addition. All right, some Cambridge questions coming your way. I know you're so excited to see how does this look on paper 4, which you'll see next class. Reading. Look at all that reading. In aromatic substitution of monosubstituted benzenes, the orientation of an incoming group depends on the nature of the group already touched the ring. What are they talking about here? Did we learn about that last class? Things we add depend on what's already on the ring. Did we talk about that? We're talking about directors here, right? So then they tell you, they're like, hey, look, if I've got a methyl group, that directs down there, 2, 4, 6, right? If I've got a CO2H, because that's an electron withdrawing group, that's going to go 3 or 5. So they're actually giving you this information. They're like, hey, look, use this information to help you with this. Use this information as an aid, and that will happen a lot of times on paper 4, where they give you stuff to help you try to figure out what's going on. Use this information as an aid. Suggest a structure for compound C in the following synthesis, which means we're trying to create 3-bromobenzoic acid. So, what would be compound C? What do you think? Yeah, it would be the intermediate you have in between, but what would it be? Think about what's going on here. They're telling you, if I've got a methyl group, whatever I add is going to add over here. I need to add bromine. But if I add bromine right now, it's going to add down there. I don't want bromine to add at the bottom. I want it to add over here. So what do I need to do first? KMNO4, right? And although they're not asking you for all of that, they're not asking you for the reagent and conditions. That is what I need to do. I need to change CH3 to CO2H first. So they're asking you basically what's the order in which things need to happen. I need to change this to that. Because if I can change CH3 to CO2H, now when I add the bromine, it is going to add to the 3rd position. So that will give you the point if you did that. Does that make sense? They're asking you what will you have to change the group to. So instead of directing 2, 4, 6, you're now directing 3, 5. You would have to change the H3 to CO2H. So step 1 would require KMNO4, OH minus, reflux, and H plus afterwards, like that. They didn't ask you for reagents and conditions to make it happen. They're asking you, how do we get to where we want to go, which is here. We needed to change the methyl group to CO2H. And here they show you the CO2H is here already, and then we add the bromine. So this is the type of question you could commonly see on paper 4 with electron directing groups and electron withdrawing groups. So now, I told you reagents and conditions were not asked, but guess what? What's asked for in the next slide? Reagents and conditions. So I just gave them to you for step 1, didn't I? To change the methyl group, the R group, to a carboxylic acid, we have to use KMNO4. This is a hard one to remember because it's a lot of stuff. For step 1, we have to do KMNO4 and OH minus, and then we have to do acidify afterwards. So it's like that.
Wait, what do you also need heat? What do you also need heat?
I had mentioned earlier, I'll tell you again. In the mark scheme that I was looking at, actually, when I was looking at the bell work, they did heat/reflux. So that means you could say heat or reflux, like you could say either, but you can always just say heat under reflux, just to be careful. So reflux would be fine, but you could also say heat under reflux, or just heat. All right, step 2. That's this one, to go from here to here. What is my reagents and conditions? How do I get that bromine there? AlBr3 is the catalyst.
and what adds the bromine. If it's just bromine, it's
BR2.
BR2. Good. It's weird that they write it on a box, but you know, it is what it is. A box makes me think that they want me to write like a product. Maybe it's to throw you off. I don't know. All right, continue. We got this. So now we're going to begin talking about phenol, but we will largely save much of phenol for next class. So we're going to start to talk about phenol now. We're done with regular benzene. Benzene, by the way, is chapter 25. Phenol itself is chapter 26. So we have finished chapter 25. The unit we're in is chapters 25, 26, 27. So we finished the first 1/3 of the content already. And so now we're going to introduce chapter 26 in the textbook, which is phenol. Spend a little bit of time on it. Let me see how far for the homework. I wonder, your homework may have disappeared. How unfortunate.
Yay. Oh.
Oh, it's online.
Oh.
Let me just double check. Oh, no, it's here. I found it. Because remember, I printed it 2 days ago. Let me double check your homework to see how far. I don't believe. Double check. Yeah, no, I have some reactions of phenol in here. So we do need to cover a few reactions of phenol. Okay, so let's get to it. Structure of phenol. Let's talk about phenol. Is phenol soluble in water? What do you think? It's got OH, but it actually turns out that it's got a lot of carbons for the amount of OH. And the way solubility works is the more carbons you have, the less soluble your substance is going to be. So what I'm trying to tell you here is that if I have CH3OH, this would be very soluble in
Why
water.
you have the less solubilities?
But the more carbons I add, this is not soluble. This is not soluble in water. 1, 2, 3, 4, 5, 6. So it actually turns out for every one group that hydrogen bonds, it can only be soluble in water for up to 5 carbons. And so this is just something I know from biochemistry. It helps you analyze very large molecules to see if they're soluble in water or not, and that works for medicine. So for large molecules, every one hydrogen bond will be soluble in water for up to 5 carbons. You may want to write this down because it actually explains a lot. And by a lot, I mean for anybody who's ever going to study biochemistry. It explains a lot. Anybody who's going to be a doctor is going to study biochemistry. To be clear, it says for large molecules, every one hydrogen bond will be soluble in water for up to 5 carbons. This explains why fats, like butter, fatty acids are like this. This is a fatty acid. You may have asked yourself, we know fats are not soluble in water. You can go home and test that yourself. You can mix oil. You can mix oil and water, they will not mix. You can put butter in water, they will not mix. The oil will form little globs.
Like the hydrophobic tail.
Because of the hydrophobic tails. So it turns out the hydrophobic's a more important factor here.
And that has to do with the exact, what I'm trying to tell you here. If the amount of carbons exceeds for this electronegative hydrogen bonding group, 1, 2, 3, 4, 5, now this is not the dominant factor anymore. The amount of carbons in the chain, if it's a large chain, becomes the dominant factor. And this is largely hydrophobic, even though it's got a little part of it that's hydrophilic. In biology, you're going to see that when you have like semi-permeable membranes, the hydrophobic parts on the inside and the hydrophilic parts on the outside. And so your groups will go through, they get like this coordination pattern that ions can go through because you've got those areas of little pathways that you have in between. But the ions are usually, not attractive to these hydrophobic tails because it's all charges. Everything is charges, has to do with charges. So the reason I'm bringing this up is because phenol is actually not predicted to be soluble. Why? Because it's got 6 carbons. Benzene is 6 carbons. What type of intermolecular force does it exhibit? It is hydrogen bonding, right? And is it acid or base? Now, this is fun. It's not what you think. Or maybe it is what you think. Who knows? Depends on where your brain's at.
It has no age.
It has a OH. These delocalized electrons in here, are they positive or negative? Negative. They're negative, right? This oxygen is also negative. What happens when a hydrogen is next to a lot of negative groups? It starts to become positive. So phenol is actually what? An acid. And it's actually very acidic, almost like a carboxylic acid. Because with the carboxylic acid, you've got 2 electronegative groups coming from the 2 oxygens here, pulling the electrons away. But for this, you have the electrons in the ring actually contributing to pulling the electrons away along with the oxygen. So phenol is actually an acid, and you should know that because that means it contributes and it participates in all acid-based reactions. So you could be given an acid-based reaction where your acid is phenol. All right, so far so good? So I think this will be our last slide, and then I'll talk to you about your homework. Review. What does pKa have to do with acidity?
Okay.
Do you remember that? It's back in Unit 1. What is pKa? It's like the pH.
But you did take the logarithm.
It's the logarithm of Ka. Ka is the dissociation constant for an acid. The lower the pKa, the stronger the acid. It actually works the same way as pH. Like the lower the pH, the stronger the acid. The negative log of Ka. But you can actually look at the numbers and compare acidity. And so what we always compare, what Cambridge is going to ask us to compare, is compare to water. Why would we compare everything to water?
Because it's a baseline. It can be either base or an acid.
This is amphoteric. By definition, water acts as an acid or a base, depending on what it's combined with. So it is basically our baseline compound to compare the acidity of other compounds to, because water is neutral by definition. So if you look at the pKa's, they're telling you some information here. What is phenol compared to water? Acid or base? Acid. What is ethanol compared to water? Base. And you should write that down. Why? So the strongest acid here is phenol. The weakest acid here is ethanol. And so looking at their chemical structure, phenol being this, water being this, and ethanol being this, can you compare? Why
according to their chemical structure, would this be a stronger acid and this be a weaker acid? What is going on? The dual-localized electrons here are withdrawing. So in phenol, the localized electrons, perfect, Diane, are withdrawing or taking electron density shifting electron cloud away from OH, which weakens the OH bond. So the idea here is it allows H plus to dissociate. So the idea here, thinking about it, is these electrons here are pulling the electron density down. The electron density is being pulled down, which means the bond between the oxygen and the hydrogen becomes weaker. A weaker bond will break easier. A weaker bond will break easier, so phenol will be a pretty good acid, at least in comparison to water. So what up with ethanol? Why is it a terrible acid in comparison to water?
No fault.
Instead of having withdrawing groups, you have something called donating groups, now that we've learned about those, right? The ethyl group that's next to the OH doesn't take electrons away, it actually puts electrons in. Do you remember that? So because that's an electron donating group, instead of weakening the OH bond, it will do what to the OH bond? It will strengthen it. And if the bond is strengthened, will that H break off? If it's bigger bond energy, it will not. So we're going to write that at the bottom. This is the last thing we're writing for the day. So in ethanol, the CH2CH3 group is an electron donator. So wait, electron donating groups and withdrawing groups are going to be a big deal. Like what I taught you last lesson is going to be a big deal in terms of explanations. We're actually going to have to explain a lot in this unit because of that. CH2CH3 is an electron donator. Which will strengthen the OH bond. And H plus will not dissociate as easily. All right, I'm going to give you time to finish writing that down. And for your homework today, do questions 1 through 5 only. So on the homework, questions 1 through 5 only. It will be due before the next class, but you don't have to do the questions with phenol because I haven't finished phenol yet. And that's why I said in the schedule, if you'll notice, we were going to start phenol today and we were going to continue with it next class. So, Unit 6 homework 2. This is the only homework I've given you all week. Unit 6 homework 2. Just do questions 1 through 5. The last question, don't do yet. I mean, unless you want to look ahead in the notes and do it yourself, you don't have to do the last question yet because I haven't finished yet. And then I'm going to go ahead and stop recording. Bye, Julio.